book called The Cosmic Cocktail chronicles the history of the study of dark matter as well as her own path as a woman in physics. Let's start by having Dr. Freese introduce herself and her work.
So I am the George Eugene Uhlenbeck Professor of Physics at the University of Michigan, and I do both research and teaching. My research is in the field of cosmology at the interface of particle physics and astrophysics. So it's how the smallest particles in the universe, the role that they play in the grandest scales of astronomy, the galaxies and clusters. I also do teaching in courses ranging from a freshman seminar in cosmology for non-scientists to quantum mechanics for physics majors, all the way up to a variety of graduate courses on special topics.
And now you've written a book called The Cosmic Cocktail.
It's been an adventure.
Right, and so the book is about the mystery of dark matter and the history of its study. Will you tell us the recipe for the cosmic cocktail?
Yeah, I was about to say, the book it's a recipe for the cosmos, and I'll just start with the surprising fact about what is the universe made of. So if you take all the objects of our daily experience, your body, the air, the radio, the walls, the planets and stars, all of that is made of atoms. But if you take all the atoms in the universe, they only add up to 5% of the content of the universe. So the big puzzle is the other 95%, and that's what I work on. We're trying to understand the dark matter and the dark energy that are the bulk of the universe. And in particular, my book focuses on the dark matter, which is what is the predominant bulk of galaxies, including our own Milky Way. So we're trying to figure out what this stuff is.
So could you quickly inventory the cosmos for us? How much of it is dark matter? How much is dark energy? How much is something else?
As far as the main constituents, it's 5% atoms, and then it's about 25% dark matter, and the rest of it, the other 70%, is the dark energy. Okay. So let me tell you about the cosmic cocktail recipe.
Yes, please do.
You have 3 ounces of dark matter, 7 ounces of dark energy, a half an ounce of hydrogen and helium gas, 0.003 of an ounce of other chemical elements, 500 ounces stars, 500 ounces neutrinos, 5/10,000 ounces of cosmic microwave background light, which is the leftover from the early universe, a millionth ounces of supermassive black holes, and all of this together is shaken, not stirred. And I would say the secret ingredient is the dark matter.
What is dark matter?
Let's talk about the Milky Way galaxy.
Okay.
So at the center of the Milky Way, there's a giant black hole. It weighs about 4 million times as much as the sun. And then you have spiral arms, like a pinwheel, and that's where all the stars are located. So if you go out along one of those arms, you get to the sun, and the sun is 25,000 light years away from that central black hole, so we're not getting sucked in anytime soon.
Oh, good.
But if you take all of that, which is when you look out at the night sky and you see that band of stars called the Milky Way, that's this pinwheel structure, and all of that is the flat plane that we call the disk of the galaxy. But now surrounding that disk, there's a giant sphere, a giant spherical object, which is made of dark matter. And that's where most of the mass of the galaxy is. So when we say dark matter, we just mean that it doesn't shine, it's non-luminous, it's not stars. It's a mystery, and we're trying to figure out what it is. And we think that the best bet for what it's made of is that it would be some new kind of fundamental particle. Not neutrons, not protons, but something altogether new. So wow, this is some kind of particle where there would be billions going through you every second. But they don't hurt you, they don't do anything to you. About one a month hits one of the nuclei in your body, but you don't notice. Because these particles, they definitely feel gravity. They're what holds the galaxy together. But they don't have electromagnetic interactions. They don't have strong interactions that hold your nuclei together. Mm. So they really don't have much. They don't have much force on you when they go through you. They might have of the four fundamental forces, the remaining forces, the weak interactions, and they might have that. That's the same force that's responsible for some types of radioactivity. So it gives you an idea of where the dark matter is located in the galaxy and in the universe, and what we think it might be made of.
So I think this will be kind of a new concept for some people, that this matter is actually more dispersed and it's not condensed into objects like planets, right?
Yeah. Mm-hmm.
Okay.
So believe it or not, without dark matter, we couldn't exist. It's the dark matter that starts the process of galaxy formation early in the universe. So when the universe was about 100 million years old, you had these dark matter particles that started to clump together. At first they made small objects that were smaller than the Earth, and then those Earth-sized objects would clump together to make bigger ones, and bigger ones, until eventually you get galaxies, and then galaxies merge together to make clusters, and you end up with the large structures that we see in the universe today. If we only had atoms, then this process would take too long, because the atoms are not able to clump as quickly as the dark matter. Mm-hmm. So it's the dark matter that actually controls and dominates this formation of large-scale structure. But then once you have something like a galaxy, the gravitational force of the dark matter keeps it inside the galaxy, but it doesn't have these other forces. It doesn't have electromagnetism. It doesn't have the strong force. And so it just stays floating around in the galaxy, whereas the atoms, they hit each other. So if you and I bumped into each other, we would get stuck. Mm. And that's what happens with the atoms. They collide into one another, and then they settle down into this flat plane, this flat disk that makes up all the stars and planets in the galaxy. Does that make sense?
Yeah, that does make sense. So how do we know it's there? Is it something that people can detect by looking at the stars or the galaxies, or is it something that's hypothesized by the mathematics?
Oh no, there's a ton of observations that prove that it has to be there. It doesn't give off light, but you can see its effects by the gravitational pull that it exerts on other objects. So if you look in galaxies, then if you watch a star moving around in a circle around the center of the galaxy, then the speed of that orbit is determined by how much mass is inside the orbit. So if you have more mass inside there, then this star goes whizzing around really rapidly around the center. And that's how this dark matter problem was first identified, believe it or not, in 1933 by a man named Fritz Zwicky, who noticed that he was actually looking at clusters of galaxies, and he noticed that things were moving too rapidly. He couldn't understand it based on the stellar material that he knew about it, the stars and other luminous objects. And so he postulated something else was pulling on it, and he called it dunkle materie, which stands for dark matter. Mm. So that was the first indication that there's something with a gravitational pull that is speeding things up. But just because he saw it in one object wasn't really enough to prove how that it's everywhere. So now we fast forward to the 1970s, where Vera Rubin and Kent Ford looked at galaxies, and they saw the same behavior in every single galaxy they looked at. They watched things moving around the centers of galaxies and saw how fast they were moving, and you have to postulate some additional material inside those orbits to explain why these things are moving so rapidly. Mm. So it was their work in the 1970s that led to a scientific consensus that dark matter has to exist.
Yeah. So I think you've kind of nicely explained dark matter for us. How about dark energy? What makes that different from dark matter?
Dark matter is a kind of matter, but by definition that means that it's attractive. So dark matter is attractive. Dark energy is repulsive. Today the universe is accelerating. That means the expansion is getting faster and faster. So something is serving as some kind of repulsive force, pushing things apart. And we label that dark energy. We don't really know what it is, so that's really just, at this point, just a name. All right, now I'll tell you another story. So in June of 2011, I was on a panel at the World Science Festival in New York, where we had 3 women talking about dark matter. I was one of them. And 3 men talking about dark energy. One of those was Brian Greene, who's a wonderful science writer. Mm-hmm. So I made the joke. Dark matter is attractive, and dark energy is repulsive, which is, scientifically speaking, absolutely correct.
So unlike dark matter, which literally is dark in that it doesn't interact with photons, dark energy is dark in that we don't quite understand it or know what it is.
Well, hold on. The dark matter, I would say, it doesn't give off. It doesn't produce photons.
Oh, I'm sorry. It doesn't
produce light. It also doesn't interact with it, but even more. It's more importantly, dark really meaning that it doesn't. It's not something you can see. Mm. The name dark energy, yeah, it just means some mysterious. It means mysterious something. That's all it really means. Okay. It is some kind of energy, but you know how Einstein's equations E equals mc squared relates mass of particles to an energy, but that connection, it really doesn't exist between the dark matter and the dark energy. They're different things. They may be related. So in my theory, they would have been related, but in general, they don't have to be. They can be just completely different things. So I think those names tend to confuse people into thinking there's more in common between the two than there really is.
And how does dark matter affect our understanding of the curvature of the universe or the geometry and the dynamics of its expansion? Or yeah.
I would say it the other way around.
Oh yeah.
It's the studies of the cosmic background light, this early leftover light from the Big Bang, taught us 2 things. It taught us the total content of the universe, how much there is, and it also taught us what the geometry of the universe is. So if you look at the microwave sky, then it's just like looking out into the sky, but our eyeballs see only visible light, but with the right kind of instrument, you could see the same thing, and you would see a microwave sky. And some parts of the universe are a little bit hotter, and some are a little bit colder, in terms of this microwave light. By the way, the microwave background is very, very cool. It's only 3 degrees Kelvin. But some parts are a little bit cooler and some are a little bit hotter. It's from the size of the hot spots that you can tell the geometry of the universe. And in Einstein's day, there were 3 possibilities. The universe could have been closed, which would have been the surface of a sphere. So it could have looked like a sphere. It could have looked like a saddle. Or it could be flat. And when I say flat, I don't mean it's a 2-dimensional geometry. I just mean that there's no curvature at all. It's like you take a cube, and you take each side of the cube out to infinity. And the ordinary geometry that you would have learned in 9th grade would apply. Parallel lines would keep going on parallel forever. And that's in contrast to a spherical geometry. If you had some creature sitting on the North Pole of a spherical geometry, if it sent out 2 phaser beams that went along the equator of the sphere, then those 2 phaser beams would come all the way back around and bite him from behind. So those parallel lines would eventually meet. But in the flat geometry, you have ordinary geometry with no curvature of any kind, and that, if you look at the microwave background and you look at the size of the hot spots, it turns out that's the kind of geometry we have. So that was one of the major discoveries I don't know, of how many centuries is scientifically huge. So we understand the geometry of the universe and the total amount of mass and energy that are contained in any volume of the universe.
And these curvatures have implications for the ultimate fate of the universe. And I have a feeling I might regret this, but what are our projections?
Well, you're absolutely right. The type of geometry affects the future fate of the universe. So if the universe had been a sphere, like the surface of a sphere, then that sphere would reach a maximum size. It would expand, reach some maximum size, and then recollapse. But instead, with the flat geometry, the same would have been true for the saddle geometry, the expansion never stops. The universe just keeps growing. And so we call that the big chill. Everything gets farther and farther apart from everything else, and it becomes more and more difficult for life to exist. And so this is something I did some work on. I can elaborate on that if you would like me to.
Sure, yeah.
Ironically, if you look into the future of the universe, life is very difficult because everything would fry to death we call it the heat death. Everything would burn up. In order for life to exist, we have to metabolize, and when we do that, we give off some kind of heat. And eventually, it doesn't matter how long, although the universe is expanding and cooling off, eventually you're going to reach this limit of the microwave background, and you still have that heat to contend with. And so the problem is that life would die in this heat death. But it depends on the type of dark energy. So my friend Will Kinney and I realized that if it's not a constant vacuum, it's not a cosmological constant, but instead, if the dark energy, the amount of it decreases with time, which would be true in a Cardassian expansion, then you can actually beat the heat death. So life can continue. Certainly not life as human beings. This I'm not saying it would necessarily be a pleasant life, I have no idea. But at least you could have some cloud of communicating things that have information stored in them and so on, and so you would be able to, life would be able to survive basically forever. So there's a quote from Philip Ball in The New Scientist, who, let's see, what did he say? The quote from him is something like, Katherine Freese and Will Kinney may not look much like superheroes, but they may have just saved the future of life in the universe. So that's what we were quoted as from.
Thank you.
That was well, of course, I do have to say this. It really takes a lot of hubris to ask questions about the infinite future into the universe, because who knows what's going to happen. So for all we know, there's a multitude of universes parallel to our own, and we're very, very clever, and perhaps we'll find some wormhole to go sneak over to some other universe where it's more habitable, or who knows. But it's fun to think about these things.
It is fun to think about these things. You're lucky that's part of your job.
Oh, I know.
So where is the data coming from right now? Have things kind of shifted from the astronomical observations to the LHC in the particle world, or are we still doing both?
As far as dark matter hunting, there's a three-pronged approach. On the one hand, it is the particle accelerator at CERN in Geneva, where you smash two protons together and you try to create dark matter particles that way. So that's a very particle physics-oriented approach. Then the second approach is in underground laboratories. This would be underneath mountains or inside abandoned mines. You put some detector there and you wait for the particles that are flying around in the galaxy to come hit the detector, deposit a little bit of energy whenever they hit a nucleus, and then you have to find that energy that was deposited. It's very difficult experiments. And then the third approach is astronomical. So here you have, well, I guess I haven't talked about this, but the favorite candidates for dark matter are particles called WIMPs, weakly interacting massive particles. These particles are their own antimatter, and whenever two of them encounter one another, they annihilate, which means that they turn into something else. So they're gone, but they don't just disappear into nothingness, they turn into something else. And one of the things they can turn into is high-energy photons called gamma rays. And here we have a satellite in space called the Fermi Gamma Ray Space Telescope, or Fermi for short. And this is looking for these high-energy gamma rays. One of the things that we're particularly excited about is that Fermi was looking towards the center of the galaxy, and that's a place where you would expect to have an extra large amount of dark matter particles, and you could have a lot of this annihilation going on. That annihilation would produce the gamma rays, and Fermi at this point is seeing an excess of gamma rays compared to what could easily be explained from other astrophysical sources. So it's possible that Fermi right now is sitting on a dark matter detection, that there is a signal from dark matter annihilation that we're looking at. This third approach of looking for these annihilation products is called indirect detection. So in all, the three prongs are the particle accelerators to actually create dark matter, or the underground laboratories which sit there waiting to be hit by dark matter, or the third astronomical approach where you're looking for the results of the annihilation of the dark matter. And what's so exciting for all of us is that we feel like we're on the verge of discovery because all of these, no, that's not true. We feel like we're on the verge of discovery because there are so many unexplained results in detectors right now that could be the discovery of dark matter. Not all of them can be right because they would be in disagreement with one another, but what we're thinking is that we're really on the edge here of figuring out this 80-year-old puzzle of what this dark matter is made of.
So what is the limiting step here? Do you just need more data, or is it just making sense of the data? What's next?
Yeah, I would say that both of those aspects. The main thing we need is more data. Right now, there are unexplained signals. There's an Italian experiment called DAMA, which is in the Apennine Mountains, underneath the mountains near Rome. And they're one of these underground experiments that is seeing the signal of a dark matter particle striking the detector. At least is possibly what they're seeing. They're using an effect that I proposed originally with my collaborators, which is called annual modulation. As the Earth moves around the sun, you would expect a difference in the count rate because you have different numbers of dark matter particles hitting your detector. And this experiment, this DAMA experiment, has 13 years worth of data, and they definitely see the signal going up and down exactly as we predicted. They always have a count rate peaking in June and a minimum in December. So that got people very excited. Oh my God, maybe they've discovered this thing. But the trouble is that they're in disagreement with other experiments. But then in trying to compare to other experiments, you have a problem. The DAMA experiment is made of sodium and iodide crystals, but the other experiments are made of different kinds of materials. So how can you possibly compare them? So here's where the theoretical side of your question comes in. In order to compare them, we have to guess exactly what kind of interaction the dark matter is having with the detector. So once you postulate one type of interaction, then you can go and make this comparison between the different experiments. So in the simplest, there's something called the spin-independent interactions. If that's true, then the DAMA experiment looks like it's ruled out by these other experiments. But what if that isn't true? So theorists are working very hard to try to reconcile positive and negative results from different experiments to see is there some new kind of theory that we haven't thought of that would be consistent with everything. So there's definitely an important aspect to the theoretical studies. The main one is data. Eventually, what we're going to see happening is you'll see the same results, consistent results between different experiments. So imagine this Fermi satellite looking towards the center of the galaxy. The particles that would be responsible for the gamma rays seen by the Fermi satellite, what if you saw those same particles in one of these underground experiments? If these two were consistent, then you would feel like you've nailed the problem. And another aspect of this are the personalities. There's a lot of very charismatic, strong personalities, and these people are going to have to concede, and they're going to have to agree, yes, we agree with what you're saying, that it would be consistent with what I'm saying.
Okay. What are you working on right now?
A few years ago, I worked with collaborators on a new kind of star called dark stars. These would be the first stars to form in the history of the universe when it was about 200 million years old. So these are probably not stars that exist today, but they would have been around very early on. And here's what would happen. You have some cloud of gas, of hydrogen and helium gas from the Big Bang that starts to collapse and is trying to make a star. As it does that, it pulls in, it's in a very dark matter-rich environment. It's at the middle of one of these spherical dark matter objects that we call dark matter halos. And so as this cloud is collapsing, it pulls dark matter in with it. And the question we ask is, well, what role does this dark matter play? Sure, it provides the gravity that allows the star to start forming, but if it is this kind of self-annihilating particle, then the annihilation products could do something to this collapsing cloud. And yes, they do. So the annihilation products, I've already talked about the photons that could come out. It's also electrons and positrons, the antimatter of the electrons. And all of these particles, as the cloud gets dense enough, these annihilation products would get stuck inside the cloud, and they would heat it up. In fact, you get a real star out of this. You get an object that's in equilibrium, just like a regular star, but it's not powered by fusion. It's not hot enough for any fusion to get going yet. It's powered by dark matter annihilation. Now, the thing that I always have to clarify about this is, despite the name dark stars, the stars are made almost entirely of hydrogen and helium with just a smattering of dark matter, a really tiny bit of dark matter. But dark matter is a very, very powerful heat source. And the other thing about the name dark stars, we didn't realize until a year after we proposed these things that they would be really, really bright. They're stars, they shine, they're not dark at all. In fact, they can grow to be 1 million times as massive as the sun and 10 billion times as bright. And if that's true, then the next generation space telescope, the sequel to the Hubble Space Telescope, and this new telescope is called the James Webb Space Telescope, this JWST should be able to see the dark stars, because they were early stars, they're really, really big and bright, powered by dark matter, and so that is, in a way, that's a fourth prong of the search for dark matter. So it's possible that dark matter could be discovered first by discovering these dark stars, which would be pretty cool. So as far as what I'm working on now, we realize that these dark stars could pulsate. That means they get a little bit brighter and dimmer over the course of a month. So if you're looking at with the James Webb Space Telescope into the very early universe, and you find a bright object that pulsates, then I don't really know of any other competitor, any other object that it could be. So this would be a sort of smoking gun, that you know what these things are, a smoking gun for dark stars. So that's what we're working on right now, is to try to really understand these pulsations. By the way, all the projects I've talked about, the dark stars, they're in the epilogue to the book. Mm-hmm. So this is mentioned in there, and I'll tell you about another project I'm working on. We have an idea for dark matter detection using DNA. So here you would have a very thin plane of gold It's a sheet of gold about 10 nanometers thick. And from this sheet of gold, there are strands of DNA hanging down. Now, when the dark matter particle comes along, it knocks a nucleus of gold out of that sheet and into the DNA. And whenever a gold nucleus hits one of these DNA strands, it breaks that strand. The broken part falls down, and you capture it, and you've set it up so that you understand the sequence of bases in that DNA, A, G, da, 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 da. So you have the full information about what that DNA looks like. And from the broken strand, you can figure out exactly where that break happened. You can make a track. You can reconstruct a track that the gold nucleus took as it moved into this forest of DNA strands. If you can track where the gold went, you can go backwards and track where the dark matter particle came from. This has two advantages. First of all, if you really see this happening, then you won't need that many counts of dark matter particles to convince yourself you really do have a discovery. And a second really interesting thing is you can go back and reconstruct what the galaxy looks like, exactly where the dark matter is, because you'll have more coming from one direction than the other. So this is a way of developing a directional detector. So it's kind of the next generation for dark matter detection.
That's fascinating. That's very, I don't know, almost science fiction.
Well, it's really fun to be working with these brilliant biologists. Yeah.
So also, before we end, I'd like you to say a few words on women in science, coming from the perspective of a successful woman physicist. What kind of advice would you give to young girls or young women considering a career in science?
One of my main messages to young women in science is pursue your passion. So if this is something that you really want to do, then do it. Don't get discouraged. I see too many young women, they get one bad grade in freshman physics and then, oh, well, obviously I can't do this, da, 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 da. Well, let me use myself as an example. I did really, really badly in freshman physics. I understood nothing, I learned nothing, I did nothing. And give it some time, and then fast forward a couple of years, and I'm learning quantum mechanics, and I'm starting to study really hard and doing really well. And so I see young women getting discouraged much too quickly. In freshman physics, you'll sometimes have students that went to very specialized science schools, and so a young woman who didn't have that background isn't going to do as well. So trust yourself, trust your passion, keep going. I really don't get discouraged. Another thing that was very important to me was a mentor. My PhD advisor was absolutely wonderful. So finding mentors, somebody you can talk to, and somebody who will teach you, both giving you a good science project to do and teach you how to wend your way through the field as through the career. Finding a good mentor is really, really important.
Great. Do you have any last words you want to say about either your book or the topic of dark matter?
Well, I guess I would say I wrote this book really for two reasons. One is it's about the science. It's about the hunt for dark matter, which is the bulk of the mass in the universe. It's a great, outstanding mystery, and it's been there for 80 years. We think we're on the verge of solving it. That's a really cool story. I wanted to tell that story. But then the second reason I wrote the book was about the fun of being a scientist, the experiences that I've had. So my personal story is in there, about how I got into cosmology and all the different people that I've met all along, the personalities, the characters, and the collaborative aspects. The fact that we are on the cutting edge of technology allows us to be creative every single day. So I go into work and I get to think of something really new and cool all the time. And that's just so much fun, and I think that's an aspect of science that really it's time that we talk about this and show this. So I guess I would end with saying those are the two reasons I wanted to write The Cosmic Cocktail, was to share